Chris, we miss you. Also, let's start with some differential equations examples. Okay, so first things first. A differential equation is what kind of an object?
It's an equation.
Fundamentally, it dang well better be an equation, right? Okay, so I think my go-to example is going to be an equation, right? Equal sign, something on both sides. And it should also be differential, which means what? Yeah, there should be some rates in it, right? Okay, so the dumbest thing I know about rates is this thing about populations. Right? And this is where I start all differential equations. I know a thing about populations. And what I know is that the dumbest way I could approach population modeling, keep in mind, right, models are guess. So this is going to be a guess, and maybe a bad one. Actually, in this case, definitely a bad one. What do I know? Well, my best guess is that the population, maybe let me write first, has a growth rate, right? And the growth rate should be what? Like, what do you think about the growth rate of a population? Does it get
Positive.
Usually positive.
Yeah, it's probably positive.
Doesn't it depend?
Yeah, it does kind of depend.
The two variables.
Yeah, there's like
People being
a
born
birth rate and a death rate, right? As long as the birth rate exceeds the death rate, their kind of growth is positive, right? So that's actually one kind of reasonable thing I could write here. I could kind of think to myself, the growth rate is really like the birth rate minus the death rate. You guys kind of on board with that? So some of you guys have not had class from me before. Are you comprehending my symbology here? Right? That's kind of thinking at this. I do that fairly often when I'm not like really sure about exactly what something is, but I want to kind of like, well, maybe this is a ballpark. Cool? All right. So growth rate's probably the birth rate minus the death rate. That seems legit. What else could I, like, what does the birth rate have to do with?
How many people are being born?
Yeah, like that's the number of people being born in a like specified time frame, right? If there are more people in the population, does the birth rate go? Yeah, it seems like it should go up, right? Does the death rate also go up? Yeah, probably. You guys see that? So kind of what I'm leaning on here is like maybe the growth rate is like, I don't know, some constant that I don't know. Times what?
A variable. Population.
Yeah, times probably the population, right? Does that kind of thought make sense? Is it true in all cases? Hell no. Right? Like, definitely not. Populations can do all sorts of weird stuff. Like, in particular, I know this is a bad model because I suspect that populations do something like this. I suspect that there's like some kind of zero and some kind of something like maybe a carrying capacity, right? And populations like start out small, right? And they grow really fast for a little while. And then they keep growing, right? And then when they get near the carrying capacity, what starts to happen? Yeah, probably it like tails off or drops back down or something weird, right? Like maybe it does something like this and like oscillates in, or maybe it does something like this and just kind of tails in. I don't know. You guys see that? But I suspect that there's some kind of like other thing going on besides this growth rate is proportional to population. You guys all see that? Okay, but let me just do the dumb thing. What's the growth rate? If I had, say, a function p, of t. What would this guy be? This guy would be a function taking what's to what's. Sorry. Back out of the growth rate for a second. What is p of t going to be fundamental? Like, what is that function doing?
Takes time and gives you how many people?
Yeah, that thing takes time and turns it into a population, right?
Yeah.
So that's going to be a function from times to populations, right? So now seven's thought makes sense. The growth rate is dp dt, right? You guys with me on that? And I just said that was proportional, right? So equals k. Still, k is a number I don't know. Times what? What's the population? P of t again, right? So this is bad notation that is prevalent in differential equations land. If I was doing extremely good notation, right, I would have these little kind of t's there, right? You guys see that? But I think I'm going to suppress a lot of those. The reason I'm going to suppress a lot of those is I don't want you to accidentally cancel. Okay? Like, this is sheer handwriting things. So just leave them off, because otherwise you might screw up and cancel some stuff. And also they'll be hella confusing when we do separation of variables. Okay? So leave those things out of there for now. Cool? All right. Now, my question to you is, do you know a function that has this property? That the derivative is basically the function you had with a constant kicked out.
Any exponential function.
Yeah, some kind of exponential function, right? Like, let me just I'm just going to think at this thing. I'm going to think like maybe p of t is e to the t, right? Okay, so, and this is the approach for solving differential equations that you guys have right now. You guys actually know how to solve a lot of differential equations right now, because you know a lot about derivatives and integrating, because you've had like Calc 1, Calc 2, and maybe Calc 3, right? You guys know a lot of stuff about calculus. So here's your guess, right? And that's really what we're going to do. Differential equations is a lot about just making an educated guess and carrying on.
What are we going to be solving for?
Good. I'm trying to solve for p. You guys see that? I'm trying to find a function for this population. You guys cool with that? I'm trying to make the model. And that's basically what we're going to end up doing. We're going to have, and we're doing this backwards actually, because I'm teaching the way we always teach. So I'm going to give you a technique, and then I'm going to like, oh, hey, here are some life things that have that as a solution. Like, write down a differential equation, and then notice that I taught you how to solve it last week. Today we're doing this the right way, which is okay, the biologist told me something about populations, and now I'm like, in the dark, guessing, how does that, like, how could I find a model for that? So my first blow was, maybe p of t is e to the t. What's p prime? P prime's e to the t. Right? Okay, so now I'm wondering, did that work? Is it true?
Yeah.
Like, is dp dt, that's this guy, right? That's e to the t, and I'm wondering, you guys see that? That's this guy. Is that k e to the t?
As long as your k is 1, you're good.
Oh, crap. Is k 1? Is the constant of proportionality 1?
You don't know.
I don't know. The biologists, do they say the growth rate is the population? Probably not very often. Right? That would be all individuals of the population give birth. Shit. That's probably not true.
It's an issue.
Right? Because like some of them are too young, some of them are too old, some of them are the wrong equipment. Right? Like probably this doesn't work. So what do I need to do? Also, it doesn't adjust for timescales, right? You guys see that? Like I would like to be able to adjust this for timescales. Like I would like to talk about the growth rate per units in days instead of units in years. And if we set the constant of proportionality equal to something, we've hardened that time scale. And I don't know what I hardened it to. You guys see that?
When you set k equal to the, when you find just any exponential function, like the general exponential?
Yeah, I need to adjust my thought, right? Like, this was my first guess, and it was a good guess. It almost got me there, because e to the t is almost k e to the t. So where do I put that k in my guess to make it so that my guess works? Like, this was my first blow. Almost. So what's your second thought? Yeah, seems like throw a k in the exponent, right? So try p of t is e to the kt. That seems like a good thought. So what's p prime then? K e to the kt. Ooh, I differentiated, right?
Oh, yeah, sorry.
But the plus some constant is a point well taken. There could be constants up in here somewhere. You guys see that? Crap. And this is where having a technique is better than guessing, right? Like, if you have a technique, you can know where those constants have to be. But let's see what we got, and then maybe we can put the constant in. Like, maybe our guess will be good enough. So, I think I got this piece, right? That's a k e to the kt. And I'm wondering, is that this piece with a k? So is that k e to the kt? Yeah, badass. So, what we say is, this thing is a solution, really just a p, right? P of t is e to the kt, is a solution of this differential equation. You guys want me to write that down so you can see it? If I'm being extremely precise, I would say, oops, wrong marker. I would say P of t equals e to the kt is a solution of, or maybe to, that would also be a reasonable phrasing, the differential equation p prime equals kp. You guys see that? Now, this point about constants is kind of a frustrating one, because I've said it's a solution. Is it the only solution?
You can slap another constant on both sides.
Oh yeah, you could you guys see this equation, right? You could multiply both sides of this equation by a constant. It would still be true, right?
Yeah.
That would be putting a constant in right here. Is that going to act right if you differentiate? What's going to happen to that constant? Like if you put in a, I don't know, p0 maybe for kicks. Yeah, it'll just chill there, right? Because the way you differentiate a constant times a function is you just leave the constant and differentiate the function. So you'll get this guy with a p0 here too. You guys see that? So I found that p of t equals e to the kt as a solution of the differential equation, p prime is kp. And if I wanted to do a better job, I could say P of t is P0 e to the kt is the general solution. Of the differential equation. P prime is kp. Now, how I know it's actually the full the full solution, that's a little tough. Without a technique, I don't know. Like, I've guessed. How do I know there's not some other option? Right?
Yeah, is there actually a way to prove that?
Yeah, but it's tough. So we're not doing it today, but we'll do it.
Oh, cool.
Yeah, we'll talk about that. So once we get a technique, there'll be, after we get technique, there'll be things called existence and uniqueness theorems. And those will tell us that what we've arrived at is the general solution, if we're in the right situation. What's up, Ken?
So did you just combine the previous K with the P naught?
Is the P naught plus the total,
So that'll be a P naught on both sides, right? One will get there here,
Okay.
and the other one is from this guy.
Wait.
oh,
But where did the K go?
Where did the K go?
Yeah. Because you had it with the P naught below.
Oh,
This is P prime.
So,
That,
okay, yeah.
the K is in the P prime.
Okay, yeah.
In the P, it's just in the exponent by itself. You guys good with this? Now, knowing it's the general solution is tough. But knowing it's a solution is pretty easy. Right? To figure out whether something's a solution, you take that thing, trot it back to your differential equation, calculate some derivatives, and then you cram them in the appropriate spot with a question mark in the middle. And then if the left-hand side is the right-hand side, you are good to go. And if it's not, then you have a problem, because it might still be the same thing up to algebraic manipulation. Right? So you might have to do algebra or trig identities or some nonsense to get them to be the same. So it's a lot easier to show that it is the solution than to show that it isn't. You guys see that?
Yeah.
Like, it's pretty easy for me to know that if I had, say, e to the t equals 1, right? Like, it's easy for me to know that's wrong. But if I have some gobbledygook with cosines and sines on both sides, I don't know. Like, they could be the same. Cosines and sines are weird. There's lots of trig identities. Right? You guys cool with that? Okay. Did you have a thing, Drew?
no.
Okay.
This did this actually address the original question though? Because there's a ceiling on that.
Oh, so this is addressed. These two have addressed this idea. These are so far bad models of population growth. These are not good population growth models. This model in particular, you might recognize as the Pert model, right? Which is generally regarded to be, by biologists, a really crappy model. It is a good model for certain things. It's an extremely good model for like radioactive decay.
Isn't
Right?
that continuous interest also?
Yeah, it's a great model for continuous interest because the way you define how continuous interest is paid is you define it that way. It's a little bit shady, right?
Yeah.
Because that's not actually saying it's a good model. That's saying it works because we use this to calculate it.
And it doesn't work too well when the stock market crashes.
Does that kind of make sense? Like, this is not actually how money works. It's oftentimes how we calculate how to pay people money. So it works really well in those situations because it is the model,
Yeah.
right? Like the reality and the model are the same. You guys with me on that? This is a bad model for like bacterial growth in a pond, except for initially. Like when you first introduce a foreign organism, this thing works pretty well. It works well until you, like this part, looks a lot like an exponential function, right? It works pretty well until you get partway to the carrying capacity, and then stuff starts to happen that's bad. But it's good for like viral loads after initial infection or something. Or like when one flea gets in your house, this is going to do a pretty, or maybe 2 fleas, I don't know how fleas work. But this is going to do a good job of predicting how the fleas grow, at least for a while. You guys cool with that?
Yeah.
Okay. And if we wanted to do better, we can.